All right, let's dive into what three-dimensional learning is in science. Some history and a picture of how we got here. When the framework for K-12 science education was created, it helped to guide the development of the next generation science standards, or you'll hear it referenced as NGSS. At that time, science education was moving away from focusing on isolated facts and procedures in science education, and instead moving towards looking at it as a wholly integrated concept. These documents help to articulate a three-dimensional model and a comprehensive approach for science instruction. Three-dimensional learning is a continuous interweaving of three elements that develops simultaneously over time: scientific and engineering core ideas, practices, and cross-cutting concepts. As such, none of the dimensions work in isolation. They must be leveraged in concert for the purpose of constructing knowledge in the science classroom. Three-dimensional learning engages students deeply in not only the important ideas of science and engineering, but in the doing of science. It is this focus on the doing of science that presents a new opportunity to help students develop the language of science. And so when we think about the three dimensions of instruction, you can see this image, and this is a pretty common image that is widespread in understanding the three dimensions. And if you're familiar with a Mobius strip, that's the image that you see in front of you. A Mobius strip doesn't have a beginning and ending and is continuously going. And so such is the case for these three dimensions, is that they're not intended to be taught in isolation, but rather integrated so that true learning can happen, not in silos, but in a more real world perspective. This graphic is also a pretty common one in that it allows us to see that the learning occurs, the instruction occurs, the assessment occurs, when all three of the dimensions are weaved together, are woven together. This helps us to define and understand exactly the bottom line of each of the dimensions. The cross-cutting concepts allow us to measure and instruct for how students think. The practices allow us for the do piece of science. And the content piece helps us guide where students should be in their knowledge. This picture right here is pretty heavy, but I was trying to think of ways to best make sure you understood where each of the different elements comes into place. So when we start up here on the left, we can look at the practices, the science and engineering practices, and there's 8 of them. These practices in the framework and the NGSS mirror the practices that scientists use in their careers and play a central role in what it means to know and to do science. Across the grades, students engage in the practices in increasingly sophisticated ways. The practices position students to collaboratively make sense of the natural world in every grade. Will students be exploring the evidence to develop a claim about what is happening, or will they look for patterns in the data? Whatever the practice, students will be engaging in it together, questioning, asking for clarification, building off each other's ideas, and revising these ideas based on their shared sense-making. The science and engineering practices frame the doing of science as a collaborative, discourse-rich activity that positions students as co-constructors of scientific understanding of the natural world. The practices provide teachers a rich opportunity to support students' language development. So when we look at those 8 practices, it's important for us to realize that those 8 practices are looked at through the lens of kindergarten as well as seniors in high school and then beyond. They're realistic in that these are the practices that scientists and engineers do in their careers. This is how the world is observed and answered. And these are definitely in order. The thing, though, about trying to create an image and understanding them is that this order that we see right here is a linear order. In reality, it's all messy and crazy because maybe I'm asking a question and defining a problem and then developing and using models. Well, then I might have more questions and defining problems. And then I go to step 3. And then I might need to do some math and computational thinking. Well, then I might have some more questions. So as we continue through this course, we'll be diving in to understand the messiness and the awesomeness all at once of the practices. Let's move over to the content. And so when we look at these content one, or sometimes they're referenced as right here, the disciplinary core ideas, this is where we think about what we typically and past has shown us what science is. There's always been the 3 pillars of science: physical science, life science, earth and space science. However, over time, it's really helped us always to remember too that we have some engineering in here. When the Minnesota Science Standards were first introduced, the ones we're currently operating on, but are referenced now as the old ones, the intention was to add engineering science or engineering standards, and we were actually one of the first states to do that. Our intention, though, was looking at it through an integrated lens. Unfortunately, the reality is that engineering became a standalone content instruction. So when we think about disciplinary core ideas, though, they're core ideas that are big ideas in science. They're similar to what we have traditionally referred to as science content. In 3-dimensional learning, the students develop these core ideas as they engage in the practices. So we've already discussed those science and engineering practices. For example, students develop the idea of erosion by being immersed in observing the effects of water flow on the land. This is a marked contrast to the traditional way of starting a unit by presenting the scientific idea and then using practices such as developing models and investigating to confirm the ideas that have already been presented, which has resulted in a narrow body of knowledge that isn't generative. The traditional method has rendered students unable to see those science ideas in a new context. And this is where the integration of content is really important. We do this with math. We create and teach the students processes in the reality that we want them to be able to take those concepts and those processes and apply them in multiple contexts, such as the way with science. We don't want to just teach about erosion within a limited silo. Rather, I want kids to be able to understand the system of erosion and the impact that it has in many different areas. The third one is cross-cutting concepts. Cross-cutting concepts refer to a set of lenses, and we look at those lenses as 7 different lenses: patterns, cause and effect, scale, proportion, quantity, systems and models, energy and matter, structure and function, stability and change. These are lenses that scientists use implicitly and that students must be taught explicitly, meaning that scientists, it's their second nature. It's what scientists have been trained to do and how they look at practices and content. For students, though, they need to be taught how to see things through the lens of patterns. They need to understand the perspective of cause and effect. They need to understand what energy and matter look like, sound like, can be like. Like the core ideas of science, these concepts must also be developed within the context of sense-making. A student who can use the cross-cutting concept can apply the lens of cause and effect to explain a host of phenomena, from explaining the sustainability of an ecosystem for native species of insects to developing a molecular model of the release of energy during a chemical reaction. So just as was the point with the different practices, the 8 different practices, such is the case for disciplinary core ideas and cross-cutting concepts, and that these are the same from kindergarten through 12th grade. Here's a more laid out look, a little clearer understanding of what the 3 dimensions are. Even though this one is labeled as Next Generation Science Standards, these pretty much mirror exactly what our upcoming Minnesota Science Standards that we heard John Olson talk about in Module 1 are going to be. So we see on the left the 8 science and engineering practices. We see in the middle the disciplinary core ideas. And then we see on the right the cross-cutting concepts. Let's focus back into the middle with the disciplinary core ideas. You see under each of the main headers, physical science, life science, earth and space science, as well as engineering, technology, and the application of science, that there are substandards, subheaders within each one of those as well. And again, each of these are K-12 applicable, so our knowledge is relevant to what a particular age child can understand and builds upon it. I'd like you to take a second right now to create a page that looks like this in your science notebook. On one side, you're going to write wrinkles. On the other side, you're going to write wonders. With my students, this is how they know whenever we are engaging with a speaker or going to be watching a video to help us understand something. We create a T-chart such as this, wrinkles and wonders. We label it wrinkles because it's the same thing as new learnings. I do a lot with my students in understanding how your brain grows, and we come to understand that our brain grows, and its evidence of growth is with the amount of wrinkles that you have in your brain, especially with the littles that we get to teach. Their gray matter is developing and growing. The more wrinkles they have, the more learnings they have. So we really call it out and label it as wrinkles. So get your T-chart ready, and I'm going to link this next video into the document. So it's going to be too challenging to watch through this presentation here. But what I want you to do is I want you to complete this T-chart, wrinkles and wonders, via watching this video.